Hello everyone. Today we're going to do some more applications of induction. First, I will do two oddball examples. These are very peculiar examples, but they're very interesting. And then Fermat's little theorem by induction. Our first problem, it's possible to make any dollar amount n, as long as n is greater than or equal to 8, by using only $3 bills and $5 bills. When was the last time you saw a $3 bill? Well, this is actually not obvious at all. And how do we prove something like this? Well, you might think there must be some technique, combinatorics or something, but actually induction works on this. So this is my statement, Pn, that I'm trying to prove. Let's see the P8, n equals 8 is going to be my base case. So how does that work? Can I do it? Yeah. I take one $3 bill and one by $5 bills, and we're done. Okay, so P8 is true. P8 is true. I have my base case. Now let's assume that pk is true. And does this imply pk plus 1? Well, before we begin analyzing this, let's think about it a little bit. Let's look at the situation when n is 9. Here, the only way to do it is to pay with all $3 bills. So three $3 bills does the job. Okay, so from this I learned two things. It's possible that all the bills are $3 because we see here for n is 9, this is the case. And also the minimum number of $3 bills in this situation is 3. So I can write it like this. When all the bills are $3, there's no 5s. There must be at least 3 or more of them. Now let's keep that in mind and begin some analysis. So let's look at case 1. All the bills are $3 bills. Okay, so what we just learned above is the following, that there's got to be more than or equal to 3 of them. So we assume that pk is true. So we have the bills which make up k, and they're all $3 bills. All right, so I have at least 3 of them. So what I can do is take 3 by $3 bills and replace them with yeah, you guessed it, two $5 bills. That's a very clever trick because this is $9 and this is $10. So when I do this exchange, I get an extra 1 into my amount, and so therefore I have my pk plus 1. pk plus 1 is true for this case. Very interesting. Now let's look at the other case. Not all of the bills are $3 bills. So not all of them are $3 bills. There must be at least one $5 bill in there. So that's interesting now. So let's say pk is true. How can I make pk plus 1? Well, I know that there's got to be at least a $3 bill, a $5 bill. We don't know actually that there is a $3 bill. Maybe there are no $3 bills. For example, you can make 25 out of $5 bills. But we know there's at least one $5 bill. So, okay, I have one $5 bill. What I can do is take the $5 bill and replace it with 2 $3 bills. And that works because this is $5, but 2 $3 bills, that's $6. So that adds an extra 1. So pk plus 1 is true. As long as pk is true, if I was able to make the amount pk, then pk plus 1 is doable also in case 2. All right, very good. And there are no other cases. If you think about that for a moment, you will see that logically there's no other possibility. And so therefore we have done it. pk implies pk plus 1 in all the cases. And so the induction step's true, the induction works, and therefore Pn is true for all natural numbers greater than or equal to 8. Don't forget that. Our base case was 8 in this problem. So that's another oddballish thing about it. The base case wasn't 1. Our next example is a trigonometric inequality. Let's say I have all these real angles here. They could be anything, positive or negative. There's n of them. Then this is true. The sum of all these absolute values of sines with the absolute value of the cosine of the sum of all the angles is greater than or equal to 1. I think it's really not obvious. Take, for example, very small angles. Then these are very small, the sines near 0. And cos will be closer, approaching 1, but I don't really know that since I'm adding them up. Well, it could be small, or it could be not that small because I'm adding many of them. And so it's not obvious why this should be greater than or equal to 1. But it is, and we can prove it. Okay, let's start with the base case, P1. And the base case looks like this, sine A1. I have only one angle, cos A1. And this should be greater than or equal to 1. I'll put a question mark. I don't really know. We have to prove this. Well, let's think about this. Sine A1, this is less than or equal to 1. So if I square this, I get sine A1, sine squared A1. Okay, and I can remove the absolute value because sine squared is always positive. But the interesting thing is that this has to be less than or equal to sine A1 because I'm squaring a number that's smaller than 1 or equal to 1. So it's got to be smaller or equal to that. So I can use this fact because now I know that this here is greater than sine squared A1. And the cos term is also greater than or equal to cos squared A1. But that's equal to 1. So this is greater than or equal to 1. And this we now know is true. So it's not just conjecture. So I have P1. Now for the induction step. Let's assume pk is true. What does pk look like? Like that, I go all the way up to ak, and then I go the sum inside the cos goes up to ak. So I'm going to assume that this is true, and I will use this. This is actually known to be true now. We are assuming that because we're saying if this is true, then we have to prove that pk plus 1 is true. All right, but what does pk plus 1 look like? It's like this. I've added this term here, and I've added this term over here. So what we want to do is in some way use this fact in here to prove this. This I don't really know, so I put a question mark. But how can we do that? Well, let's examine what we do have. We have this sum, and that's the same as this. So if we could just add this thing to both sides, then we are able to use pk. So I'm going to do that. I'm going to write that all out. It's really, believe me, it's really tiresome to write these expressions with all these little dots and absolute values, believe me, especially when you're trying to write them and not make mistakes. All right, and there was a mistake. Okay, so now I can apply my pk because this is pk. So this is going to be greater than or equal to 1. So if I replace this by 1, then I'm okay. I'm okay because if this is still true, now this is a very subtle point. If this is still true when I replace this with 1, then of course it's going to be true when I put back this whole expression here in the yellow. Do you see what I mean? So if I prove it for a narrower case, if I make this here smaller by replacing it with 1, and if I can still prove this, then we're okay. All right, so let me write out what happens when I use pk now. All right, we get this, and we can cancel out the 1s. And now we can do some very interesting tricks here. Let's call this, we'll call this x. And this whole thing here, we'll call this y. And so this entire angle here is y minus x, yes? And so I end up with the following thing that I want to prove. Sine a k plus 1, or what am I doing? Sine x plus cos y, absolute value, greater than or equal, I must prove this, cos y minus x. So how can I do this? Well, I use trig identities, yes? I use one of those addition rules, and I get this. Now I am going to use something called the triangle inequality, and it looks like this. A plus b, all under the absolute value, is less than or equal to a plus b, like this. This is a fundamental inequality in mathematics. Now, if you want to know more about this, write me a comment in the comments, and maybe if I have time, I would do a video on triangle inequality, reverse triangle inequality, and other such inequalities. They come up all the time. They're very, very important in mathematics. It would be good to do a video on it. If people are interested, let me know and I'll do it. Okay, so take the absolute value of both sides and now apply the triangle inequality like this. And I can actually take my absolute values across the factors, okay, because they're distributive across factors. Sine y, sine x. Okay, now let's look at what we have. This is close, but we have these extra trig functions. So now you're about ready to say, well, I give up. I don't know what to do next. But let's think about this. Cos x absolute value has to be less than or equal to 1. And sine x absolute value has to be less than or equal to 1. So if I replace some of this by 1, watch what happens. Let's replace this by 1. Well, of course, this entire product is going to be larger if I do that because of this. So this is bigger, cos y times 1. And if I replace this by 1, this whole thing becomes larger than what I had before, because 1 is greater than or equal to sine y. Sine 1 times plus 1 times sine x. And so look at this. We did it. We did it. We have it. This is exactly this. And so it's true. So this is true. That means this is a stronger inequality, and that means that this must be true way up here. Where was that? This must be true when I put this back, because this thing is larger than 1. Yes, this is larger than 1. So it must be even more true, right? So we're done. We did it. So, okay, let's change color. pk implies pk plus 1, and we're done. So it's proved for all n. Pn true for all n in. And what an amazing proof. It has many little interesting techniques. I think you should do this proof over and over a few times until it becomes second nature. And now what you've been waiting for, Fermat's very famous little theorem. So it goes like this. Suppose n is a natural number, and suppose p is prime. P is prime. Then what Fermat's little theorem says is that p always divides n power p minus n. Now, there are many very interesting proofs of this. And the one that's the most common that I've seen is the one about the necklaces and bracelets that form a circle. That's undoubtedly a very interesting proof, like a combinatorial proof. But I want to show you the proof by induction for this, which I think is probably the best example of induction I've ever seen. It's really beautiful, and you'll never forget it. And you will be able to prove Fermat's little theorem anytime you need to. So let's start with the base case, P1. So n is 1. So when n is 1, n power p, n is 1, so it's 1 power p minus 1. So that's 0, and p divides 0. So okay, P1 is true. There we go. Base case is true. So now let's look at the induction step. So we assume that pk is true. And pk looks like this. P divides k power p minus k. All right, so we want to show that this implies pk plus 1. But sometimes we often need to look at the form of pk plus 1 to see how we can apply pk. So pk plus 1 looks like this. P divides k plus 1 power p minus k plus 1. Like so. So what I can do here is use binomial expansion to expand this part out. So I'm going to take this entire expression and apply binomial expansions to it. So what I did here is I just took this and I expanded it like that, as you know how to do. And here is where things start to become beautiful. Let's take the first term of this sum and the last term of this sum. Let's separate them out. So have a look at what I've done here. I've taken out the j is 0 term here, and I've taken out the p term here, j is p term here. So the sum is now from 1 to p minus 1. So this is just 1 plus sum of j is 1 to p minus 1, pj, kj, power j, and this is 1, p choose p is 1, so this is plus k, p minus k minus 1. So okay, this cancels with this, and what do I get? Well, I get something very interesting here. Notice that I have this, so I can apply pk. So I can assume here that p divides k, p minus k. And what I need to prove is that p divides this entire expression here. So I know it divides this. So now, if I can prove that p divides this thing here, then I'm done. Because if p divides this, which I know, and p divides this, then p divides everything. And so p plus k plus 1 is true. So I just have to find a reason why p divides this. Little p divides this prime. Okay, why is that? All right, let's write out this coefficient carefully here. We get this expansion. Now it looks that, yes, p does divide this because I have a p here. So it's tempting to say, yeah, sure, it does divide. But how do I know I don't have a factor of p in the denominator? If I have a factor of p in the denominator, then this might not be true because this might cancel out. If I have a factor here of p in here somewhere, then this would cancel with that, and it's not true. So I have to be careful about this. How can I argue this? Well, all these numbers, okay, all these numbers j, let me get my color back, j is less than or equal to p minus 1. Well, it's not possible for p to divide any of these numbers because p is prime. Okay, so p cannot divide any number that's smaller than p. So p does not divide this. And so therefore, this does not cancel out. Does not cancel out. And so therefore, this is true. Okay, therefore, P divides some j is 1, P minus 1, Pj, Kj, and I'm done. So therefore, Pk plus 1 is true. We used Pk over here. We applied Pk here, and we showed that Pk plus 1 must be true if Pk is true. And that means Pn is true for all natural numbers. Very beautiful. I think it's an amazing proof, really. I like it a lot. Probably like it better than the necklaces proof, which is very hard to sort of talk about because you got to draw all these things with colors and stuff. This is a lot easier to communicate to someone. I hope you enjoyed these examples. There was a viewer who asked me to present some esoteric applications of induction, and well, these are a little bit on the esoteric side because they're pretty weird, but I think I will do a future video about strong induction, which has some very peculiar applications, and also reverse induction, the Cauchy form of induction, and there's a lot more to it. And induction is used in a lot of weird ways beyond what I've shown you here, and I hope to do a video really focusing on esoteric uses of induction. Well, that was a lot of fun, and I will see you next time.